Welcome to today's probability lesson on making predictions. Probability is a really great skill for predicting what's going to happen in the future. It's extremely useful. So let's dive in and look at 3 different examples. So please do this with me on your notes. Here we go. Problem number 1. In this bag of jelly beans that you see right here, there are 40 jelly beans and 5 of them are black. How many do you predict, if you got more jelly beans, how many would you predict to be black in a bag of 80 jelly beans? Or how about 160 jelly beans? So let's go ahead and set this up. First, we want to write down what is our probability, our theoretical probability of drawing a black. Well, in this bag, we know that 5 are black out of 40 total jelly beans. So the theoretical probability of me drawing a black out of this bag is 5 out of 40. All right, so what if instead of having 40 jelly beans, if this was a good example of what was to come and a good predictor, how about if I had 80 jelly beans? So what do I notice happens when we go from 40 to 80? Let's see. Well, I notice that I am doubling the size. So I have twice as many jelly beans, or I'm doing 40 times 2 to get to 80. Well, if I'm doubling the number of jelly beans, it makes sense that I would also double the number that would be black. So what we do is we look horizontally, and if we multiply the number of jelly beans by 2, we're going to multiply the number of black by 2 as well. So I would predict that out of 80 jelly beans, now 10 of them would be black. So to set this up, you just make your first probability, 5 out of 40, equals, and another fraction bar. Figure out what do you do to get from 40 to 80 by multiplying, and 5 times 2 then would be 10. All right, so let's go ahead. What if we had 160 jelly beans? Well, I could start with my 40 again and say, how do I get from 40 to 160? What do I do? Well, I see that 40 times 4 is 160. So if I have 4 times the number of jelly beans, then it makes sense that I would also predict to have 4 times the number of black jelly beans. So 5 times 4 would be 20 black jelly beans. So I can use my probability, my theoretical probability of drawing a black to predict how many blacks would be out of 80, how many would be out of 160. Or if we want to think about drawing jelly beans, if I draw 5 for every 40 that are in the bag, then I would probably draw 10 for every 80 times I draw the bag, and probably get 20 black jelly beans for every 160 times I draw out of the bag. So that is some ways that we can make predictions. Let's move on to number 2. And if you need more time with number 1, then just go ahead and go back and pause it and get caught up with me. Problem number 2. This is an experimental probability problem. George is doing an experiment. George picked some apples at the apple orchard. For every 8 apples he picked, 1 had a worm in it. How many apples can he predict to have worms if he picks 64 apples? How about if he picks 80 apples? Let's give this a try. So we're going to set up this probability, this fraction. The numerator is going to be how many apples had worms, and the bottom is going to be the total apples that he picked. So let's go ahead and take a look, and I'm going to actually highlight the important information. We want to highlight the apples with worms. I know that 1 had a worm for how many total for every 8 apples that he picked. So let's fill that in. 1 wormy apple for every 8 apples that he picked. So basically, in his experiment, 1 out of 8 apples had a worm in it. All right, well, what if we have picked 64 apples? How many would we predict to have a worm in it? Well, let's take a look at how we get from 8 to 64. I know that 8 times 8 is 64. So if we have 8 times the number of apples total, I would expect that there would be 8 times the number of apples with worms. So 8 times 8 is 64. 1 times 8 is 8. So for every 8 apples, 1 has a worm. So I predict that out of 64 apples, 8 would have a worm. Let's try this one. How about if we pick 80 apples? Again, let's look at how do we get from 8 to 80. I see that that is 10 times the number of apples that we started with. So if he picks 10 times the number of apples, then I would also predict that 10 times the number of apples would have a worm in it. So 1 times 10 is 10. So let's summarize. Out of 8 apples, he found that 1 had a worm. We predict that out of 64 apples, 8 would have a worm. And out of 80 apples, 10 would have a worm. Now, we can prove that these are all equal to each other by simply changing these to a decimal. So if I did 1 divided by 8, and 8 divided by 64, and 10 divided by 80, we would get the same decimal every time, which is going to be 0.125. So that proves that these are equal and these predictions make sense. If you need more time to think about that, then go ahead and pause the video and finish working out how many apples would have a worm if you pick 64 or 80 apples. All right, let's go to the last problem. This is a different type of prediction problem. Let's read it. So Kira was waiting at her bus stop, and she watched these 5 cars drive by. She was paying attention to what color they were. So my first question is, of these 5 cars that drove by, so that was her experiment, to watch cars driving by, and she wanted to know what was the experimental probability of the car that drives by to be green. So what was the experimental probability of a green car passing her house? So let's look what happened in the experiment. In the experiment, we have 5 cars that drove by, so 5 total cars. In the experiment, we see that 1 of those cars was green. So the experimental probability of a green car driving by is 1 out of 5. Let's change that to a percent. So I would do 1 divided by 5, which gives me 0.2, and then we do that times 100. So that gives us 20%. So there's a 20% chance that the car that drives by is going to be green. That's what happened in her experiment. So let's look at this next question. If 20% of the cars that drove by, or 1 in 5, were green, what is the probability that the next car will be green? Now we want to do this based on what has already happened. So if 20% of the cars that drove by were green, then we know that there is a 20% chance that the next car will be green, or we would expect that the next car to drive by would have a 1 in 5 chance of being green. So the reason we do an experiment is to see what percent chance does it have of happening, and that's going to help us determine what percent chance I have that the next car will have the same results. So these two questions have the same answer. In her experiment, the experimental probability of a green car driving by was 1 in 5. The probability that the next car will be green then is 1 in 5, or 20%. Let's look at this last question. So if 100 cars drive by, how many of those do you predict will be green? So let's set this up. The bottom, remember, of our probability is the total number of cars, and the top is going to be our desired outcome, how many were green. So in our experiment, 1 out of 5 were green. So how many out of 100 total cars would you expect to be green? Well, let's look at how do we get from 5 to 100. And I know that that's times 20. We could work backwards and do 100 divided by 5 is 20. So if I have 20 times the number of cars that drive by, then 20 times the number should be green. So 5 times 20 is 100 total cars. 1 times 20 is 20 green cars. So I would predict that 20 would be green. So that is going to be how you're going to predict. We'll do more practice in class, and good luck.